Okay, we are going to look at an example here of curve sketching. Now this one's probably a little more difficult than one you would see on a test or quiz. It's got a couple different situations in it that make it a little more difficult, maybe with specifically the slant asymptote. We'll get to that in a little bit here. So first things first, we want to start with, excuse that bell, we want to start with finding the zeros of the function. So we're literally going to find out when the numerator is equal to 0. So I can do that by factoring a 3x out, and I'm left with x squared minus 16. When does that equal 0? Well, when x is 0, and also when x is plus or minus 4. So we end up with 3 x-intercepts. Okay, we also want to find the vertical asymptotes. That occurs when the denominator is equal to 0. X squared minus 4. When does that equal 0? Because that tells us what x cannot be. So we have 2 vertical asymptotes. We want to check for horizontal asymptotes. Well, in this situation, the numerator is larger than the denominator. So if I would think of the limit as x goes to infinity or negative infinity, I have 3x cubed minus 48x over x squared minus 4. So we'll multiply by 1 over x squared, and 1 over x squared, a fancy form of 1. And when I do that, I get 3x minus 48 over x. And the denominator, I get 1 minus 4 over x squared. Well, as I go to infinity, that disappears, and I have 3 infinity over 1. That equals infinity. Okay, so there is no horizontal asymptote. But since the degree in the numerator is only 1 larger, cubed versus squared, we're going to have a slant asymptote. In order to find a slant asymptote, I need to think of my denominator as 2 linear functions so that I can properly do synthetic division. So I'm going to use a 2 first because that makes this 0. And I have my 3x cubed, 0x squared, minus 48x plus 0. Bring the 3 down, multiply by 2. Add, multiply by 2, add, multiply by 2, add. Okay, now I'm going to use negative 2. So this is currently a quadratic. Bring the 3 down, multiply by negative 2, add, multiply, multiply and add. And now I have my linear expression. My slant asymptote is y equals 3x. Okay, so that's a little tricky part because you need to do synthetic twice in that situation. Okay, a slant asymptote is just that, a line that's on a slant. Okay, so it has to be linear. Alright, so there's the non-calculus portion. You can consider the limits, maybe a little bit of calculus. So now let's look at the first derivative. The first derivative of this function.
Please pardon the interruption. This is a reminder for all students. Please check your appointment cards or the posted times in front of the guidance office for your appointment for scheduling. It's very important that you're prompt for your scheduling appointment. Thank you.
Sorry for that interruption on the loudspeaker there. I actually paused the volume instead of the video, so a little delay there. My apologies. So the first derivative, and check to confirm that you can actually get this derivative. I already took it ahead of time. Comes out to this. So we got to find our critical values. Well, this is always positive. No critical values from that. It'll never be 0. So points in non-differentiability end up being 2 and negative 2. So number line, negative 2 and 2. Remember, we said the numerator is always positive, right? 3 and a positive number, always positive. Denominator is always positive too. So this is an easy one. Plus, plus, plus. Always increasing. No relative extrema. Okay, let me scroll down. And we'll do a second derivative now. Again, I took this ahead of time. Confirm that you can actually get the second derivative though. Comes out to negative 72x, x squared plus 12. And x squared minus 4 cubed. So critical values, we get 0 from right here. This is always positive, and then from the denominator we get plus or minus 2 points in non-differentiability. So we have to test. This is always positive, so I don't even care about that. If I put a -3 in, I get a negative times a negative, that's a positive. Put a -3 in, I get 9 minus 4, that's positive. So positive over positive, certainly positive. A -1, something from this region, I get a positive. Over a negative, right? 1 minus 4, that'll be negative. Put a 1 in, my numerator is now negative. My denominator is also negative, so that makes it positive. And if I put like a 5 or a 3 or whatever in there, I get a negative over positive. So I'm certainly jumping around with concavity. And at this point, we're ready to sketch. Remember, there were no relative extrema. We do have a couple points of inflection. In fact, we'll look at that a little bit later, but we have points where concavity changes, but because they're vertical asymptotes, they're actually not points of inflection. So we're ready to sketch it. Try to make it as nice as I can here. So y equals 3x, remember, was our slant asymptote. And remember, slant asymptotes, horizontal asymptotes, they all deal with x as it heads to infinity. All right, so in the middle here, the slant asymptote has no bearing on my graph. It only matters as x heads out this way more. So in other words, as I go along the asymptote, x is heading further to the left or the right. I need to drag it along the asymptote. If you notice from above, if you remember from above, -4 and +4 were zeros, as was 0. So I'm going to mark them on my graph. I had no extrema though. Okay, -2 was a vertical asymptote, and so was +2. Okay, now my graph was always increasing. That's up here on this number line there, right? All pluses, always increasing. Sorry, some stuff disappear. Watch this little magic. Forward and back, and everything will be back where it was. So I'm always increasing. Keep that in mind. Now I'm increasing and concave up. Remember, I need to go along this asymptote. So this asymptote extends, obviously, but I need to cross -4 here, so I need to be increasing and along -4. Now this, as it goes down further to this direction, will get along that asymptote. I just couldn't do it very nicely here. Okay, we're increasing and concave down, and then increasing and concave up in the middle here. So increasing and concave down, increasing and concave up, and increasing and concave down. For this part, again, my asymptote, it's going to be tough for me to hit that asymptote there from this perspective, but you know, it's going along like that. Of course, I want to hit that as well. So let's look at what this looks like on an actual calculator to get a little better idea. And you'll see why it's hard to drag along that slant asymptote there. So our original function, remember, was 3x and x, 3x and x squared minus 16 divided by x squared minus 4. And then we had 3x as our slant asymptote, so I'm going to have that being dotted lines. Now my window, we'll go the -10 to 10 here. And we'll graph it like that. So there's that somewhat of a curve. There's the middle, it doesn't even look like a curve. And there's our other one. Here comes our slant asymptote going through there. So notice it is kind of far away. Now, I know this centerpiece doesn't quite look right, so let's asymptote. So now you're going to see the 3x line really come through, and there's our curvature. That's what we wanted. Okay, so that's what we're looking at there. There's our graph from the calculator point of view. Alright, hope that helps a little bit. I'll enlarge this one a little bit here so you can see how perfect ours was. Okay, you got the idea. Hope you enjoyed the video.